You bought the car to save the planet. That was the whole point. No exhaust pipe, no trips to the petrol station, no guilt every time you turn the key. But there is something nobody told you when you drove it off the forecourt. Something that is quietly becoming one of the most complicated problems in the history of transportation. What happens to the battery when it dies? Not the car. The battery. That enormous, heavy, chemically dense block sitting beneath your feet right now. The one that makes everything work. The one that, one day, will stop working. And when it does, the question of where it goes will reveal a truth about electric cars that the industry has spent years dancing around. Here is what you need to understand first. An electric vehicle battery is not like the battery in your TV remote. It is not like the battery in your phone. It is a lithium-ion pack the size of a dining table, weighing anywhere from 300 to 700 kilograms, containing thousands of individual cells, laced with cobalt, nickel, manganese, lithium, and a cocktail of other materials pulled from the ground at enormous environmental cost. It is an engineering marvel. And it has a lifespan. Most manufacturers guarantee their battery packs for 8 to 10 years, or around 160,000 kilometers, whichever comes first. After that, performance degrades, the range drops, the charging slows, and at some point, the battery is no longer useful in the vehicle. That point is coming. Fast. Because the first wave of mass-market electric cars sold in the early 2000s are now approaching end of life, and the industry is not ready. To understand why this matters so much, you need to go back to where these batteries come from. Researcher Thea Riofrancos at Providence College has spent years mapping the supply chains that feed into electric vehicle production, and what she found is not comfortable reading. Lithium, the element at the heart of every battery, is extracted primarily from 3 countries: Australia, Chile, and Argentina. In Chile and Argentina, it is pumped from beneath ancient salt flats in a process that consumes extraordinary volumes of water in some of the driest places on Earth. Communities near extraction sites have raised alarms about aquifer depletion and ecosystem damage for over a decade. Cobalt is even more fraught. More than 70% of the world's cobalt comes from the Democratic Republic of Congo, where Amnesty International documented in 2016 that a significant portion of artisanal mining involves child labour. The industry has pushed hard to source cobalt responsibly, and battery chemistries that reduce or eliminate cobalt are advancing rapidly. But the legacy of those early supply chains is already embedded in millions of batteries now approaching retirement. So you have a battery built at significant environmental cost. It works for a decade. And then what? The honest answer right now is that nobody has fully solved this. And that is not a fringe opinion. It is the conclusion of the International Energy Agency, which in its 2023 Global EV Outlook noted that battery recycling infrastructure is scaling far too slowly relative to the volume of batteries expected to reach end of life over the next decade. There are 3 paths a dead EV battery can take. The first is second life deployment. When a battery degrades to around 70 or 80% of its original capacity, it is no longer ideal for a vehicle. But 70% of a very large battery is still a great deal of stored energy. Companies like Nissan partnered early with the Sumitomo Corporation to repurpose old Leaf batteries into grid-scale energy storage systems, essentially stacking decommissioned packs together to create giant rechargeable power banks that can store solar or wind energy. BMW and Volkswagen have pursued similar projects. This is the optimistic path. The battery does not die, it just changes jobs. But second life projects face real limitations. Every battery ages differently, depending on how it was charged, how often it was fast charged, what temperatures it experienced, and what chemistry it uses. Sorting and certifying these packs for reuse is labour-intensive and expensive. And as battery technology evolves rapidly, older chemistries quickly become incompatible with newer systems. The window for second life deployment is narrower than it sounds. The second path is recycling. And this is where things get genuinely complicated. Recycling a lithium-ion battery is not like recycling an aluminium can. It requires shredding the battery down to a black powdery material industry insiders call black mass, which contains a mixture of lithium, cobalt, nickel, manganese, and other compounds in a form that must then be chemically separated and purified before the materials can be reused. This process is expensive, energy intensive, and still largely unprofitable at current scales. Professor Linda Gaines at Argonne National Laboratory in the United States has been one of the most cited researchers on this problem. She has argued for years that the economics of battery recycling only work when the value of recovered materials exceeds the cost of the recycling process itself. Right now, for many battery chemistries, that equation barely works or does not work at all. The lithium recovered is worth less than the cost of recovering it. Cobalt is more valuable, which is why recyclers have historically prioritized cobalt-rich chemistries. But newer batteries, including the lithium iron phosphate cells, now widely used by manufacturers like BYD and increasingly by Tesla, contain no cobalt at all. Recycling them is harder to justify financially. Several startups are racing to change this. Redwood Materials, founded by former Tesla Chief Technology Officer J.B. Straubel, is building large-scale recycling facilities in the United States with the goal of recovering enough material to supply a significant portion of new battery production domestically. Li-Cycle, a Canadian company, developed a process called spoke and hub recycling that avoids some of the hazardous conditions involved in traditional shredding. In the United Kingdom, Recyclers Group is processing battery packs from multiple manufacturers. The infrastructure is being built, but it is being built against a deadline that is already approaching. The third path, and the one that keeps researchers awake at night, is landfill or improper disposal. A battery that is not economical to recycle and not suitable for second life use has to go somewhere. And without mandatory enforced take-back schemes and a recycling market that actually covers costs, some of those batteries will end up exactly where they should never go. In landfill, lithium-ion batteries can leak electrolyte, corrode, and in some cases ignite. They are classified as hazardous waste in most jurisdictions, but enforcement is inconsistent, particularly in markets without strong regulatory infrastructure. The European Union has moved faster than almost anyone else on this. In 2023, the EU passed landmark battery regulation that will require all EV batteries sold in Europe to meet minimum recycled content thresholds by 2030, rising significantly by 2035. Manufacturers will be required to take batteries back at end of life and ensure they enter certified recycling streams. Carbon footprint declarations will be mandatory. It is among the most comprehensive battery legislation in the world. China, which manufactures the majority of the world's lithium-ion batteries and dominates much of the supply chain, has also put extended producer responsibility schemes in place, though enforcement has historically been uneven. The United States, through the Inflation Reduction Act of 2022, began directing significant funding toward domestic battery recycling, partly for environmental reasons and partly for national security reasons, given how much battery material currently flows through Chinese supply chains. But legislation, even strong legislation, cannot conjure recycling capacity overnight. The International Energy Agency estimates that by 2040, end-of-life EV batteries will amount to around 14 million tonnes of material globally. The recycling systems that will handle that volume are still being designed, funded, and built right now. Here is the thing that rarely makes it into the brochure. Electric vehicles are almost certainly better for the climate than petrol or diesel vehicles over their full life cycle, even accounting for the emissions associated with battery production and the electricity mix used to charge them. Study after study, including landmark analysis by researchers at Transport and Environment in Europe and the Union of Concerned Scientists in the United States, has confirmed this. The carbon break-even point, the moment at which an EV has offset the emissions involved in manufacturing it, typically arrives within 2 to 3 years of driving in countries with moderately clean electricity grids. In countries with very clean grids, it arrives faster. This is not in doubt. But climate performance is not the only measure. Mining impact, water use, labour conditions, waste generation, battery fire risk during transit and recycling, and the sheer logistical complexity of managing millions of massive chemical packs at end of life. These are separate problems that a lower tailpipe number does not automatically solve. The battery problem is, in many ways, a preview of a larger challenge. Every technology transition creates its own waste stream. The world learned this with solar panels, which contain lead and cadmium and are beginning to reach end of life in large numbers. It learned it with electronics, with the billions of phones, laptops, and tablets that end up in informal recycling operations in Ghana and Bangladesh. The pattern is consistent. Technology scales faster than the infrastructure needed to close the loop. Researchers like Gavin Harper at the University of Birmingham have argued that the solution is not simply recycling, but a fundamental redesign of batteries from the start with end of life in mind. Batteries that are easier to disassemble, chemistries that are more benign, standardized form factors that make sorting and processing cheaper. Design for circularity, as it is called in materials science, means building the exit strategy into the product before it is ever sold. Some manufacturers are starting to move in this direction. Redwood Materials is now partnering with battery manufacturers and car companies to design future packs so that the materials can be efficiently recovered and fed back into new batteries, creating what they describe as a closed domestic loop. If that vision succeeds, the battery in your next electric car could contain lithium and cobalt recovered from the battery in your current one. You bought the car to save the planet. That instinct was not wrong, but saving it turns out to be more complicated than swapping one engine for another. The lithium beneath your feet connects you to a salt flat in Chile, a mine in the Congo, a recycling facility in Nevada, and a policy debate in Brussels. What happens to that battery when it dies is not someone else's problem waiting to be handed off. It is the next chapter of the same story you started when you signed the papers and drove away. The car is silent. The question is not,